Okay, so we're going to continue on today, learning more about spatial analysis. Oops, made my wrong monitor disappear. So what we looked at in our previous workshop, Basic Spatial Analysis, was focusing on vector data. So we did things like use extraction tools. So we clipped parts of our data like a cookie cutter, cuts out part of cookie dough. We extracted based on location. So we know we can query both attribute tables and also query using location relationships. We
Are you still here? That's already open.
Spatial join.
I just sent you an email.
Focus more on raster data. For a lot of you, especially those who work in natural sciences, you will very often deal with raster data in one form or another. So this will give some examples of how to perform our geoprocessing tasks on those data. So we will look into things like properties of rasters as a review, look at raster overlay as opposed to vector data overlay. We'll reclassify rasters and use a raster calculator. And we're going to look at all of those things through the eyes of a photovoltaic suitability analysis. So this is a classic problem in GIS called a site selection problem. This is where you're going to evaluate a set of criteria to determine if a location is suitable or not for some purpose. I have some other examples here, potentially delineating watershed boundaries out of a set of elevation data, interpolation in GIS. So you can determine values between your data, whether you're going to interpolate a raster surface from a set of points or generating contours from a raster data set. So converting rasters back to vector. So just to quickly review, what is spatial analysis? This is some sort of formalized way of examining the locations, the attribute information and relationships of features in our spatial data. We do this to address questions, to learn some new information or extract or create new information as new data sets. So this was all about solving problems, addressing questions. We talked about the spatial analysis workflow. We want to set up our problem, explore our data, put together our method. If we think back to that tiger bird, we previewed the data, we figured out what our workflow would look like through those data to get a final result, perform the analysis, and then view those results. And we also learned a little bit about what this spatial geoprocessing means. This is when you are combining together one or more data sets with one or more processing tools to link together a full sequence of processing steps. And so this is, we'll do examples of this today where we're going to work with lots of different data and analyze them in a full workflow like you see here at the bottom of the slide. So as we transition from vector overlay and vector analysis like we did before into rasters, I just want to point out some fundamental differences between the two. That vector data are actually fairly complex in the type of spatial relationships that they can model. So you can do things like containment, you can tell overlap, partial or total overlap between features, you can infer directionality, chirality or that handedness. These are things that you can represent within the vector data model. And that complexity tends to lead to very slow, long calculations for a computer. So the opposite to that is rasters, which if you remember are these grids of uniformly sized cells. Computers love to just take grids of numbers and perform calculations on these grids. That's what they excel at. So raster overlay, in a lot of cases, is much more efficient computationally. Let's think back about our raster data. What was the important takeaway we talked about in the introduction to GIS workshop? We think back, comparing raster and vector data. What type of entities did we model with vector data and what type with raster data?
Vectors, like discrete areas.
Yeah, so vector data we used to represent discrete phenomena. So things that can be described using coordinate pairs, whether they be points, lines, polygons. So opposed to that, what about our raster data? What types of entities do we model using a raster?
Continuous data.
Continuous data, so things that are very continuously over the Earth's surface, things like precipitation, temperature, elevation, land use, all of these things we're going to model as a raster. Whoops, went too far. So a raster, again, is this continuous grid of uniformly sized cells. Rasters, just like vectors, have a coordinate system along with a geographic datum and a projection along with it. We georeference a raster by specifying the location of the upper leftmost cell in that raster. So that has defined coordinates. Then just by using the cell size, we can determine the coordinates of every other cell within that raster data set. So the cells are typically square. You often see, say, a 30 meter by 30 meter raster, 10 foot by 10 foot. And we see lots of different formats. Often they look like images, things like TIFF, JPEGs, they might be grids, BILs, all sorts of different formats. Questions so far? Rasters. Let's take a look at them in a bit more detail. So the first thing we're going to do is look at two different elevation data sets, or you often see the term DEM is a digital elevation model. So these are rasters where each cell represents elevation of the land surface. There will be two different DEMs we're going to look at, and we're going to just analyze some of the properties of these rasters. So I'll open ArcMap to that document, my intermediate spatial analysis tutorial document. So I just double-clicked here to open that intermediate spatial analysis tutorial. I'm going to close. Whoops. ArcMap is going to freeze on me. Working. Okay, here it goes. So here is our data set. We're going to look at two of these rasters to start with. So the one that should come up by default is this scdem.tiff. You can then click and turn on this other layer called the South Carolina DEM. And so you notice that they look fairly similar. There's some slight difference in their color just due to the symbology, but these two layers are both elevation models that cover South Carolina. So what we want to do is take a look at the different properties of these rasters here. So we're going to try to find out some more information and understand what, say, the format, the pixel depth, where to go to determine the coordinate system and the units on it. So let's right-click and open the scdem.tiff. Let's open the properties for it. So I'll right-click my scdem, open my layer properties. And what I'm looking for is this source tab. The source tab has lots of information about our raster here. And so what I want to do is going to move this here. I want you all to tell me what the values are for all of these properties, and then we'll talk about what they mean. So let me put my screen up here. So as you look through the properties, tell me what the format you see is for this SEDEM.tip. It's a tip. So its format is that it's saved somewhere on that machine as a file with a .tip extension. How about the pixel type? Floating point. So what does floating point mean? Anyone know? So a floating point is one of a variety of different ways you can represent a number on a computer. So a floating point is one that can store a decimal somewhere in the number, as opposed to something like an integer, where the computer would only store values that are whole numbers, integers. So this is a raster where the values in the cells can contain a decimal. What's the pixel depth? 32-bit. So what that's telling us is that every value, every number that's stored for that raster uses 32 bits of storage on your machine. And that also tells you how many different values you can represent with that specific, So the formula is that you have 2 to the whatever different numbers you can store. So a 32-bit floating point can store, I'll have to check my notes, any number between negative to positive 3 to the 38th. So very, very tiny numbers to very, very large numbers. The downside is it takes up a little more memory to represent every one of those numbers. Does that make sense? What's our cell size? 30. And what's the unit on it? Sorry? 30 what? That's the size of 1 pixel. So each cell has some length and width. How about this? What's the coordinate system for that data set? Or the projection?
UTM 17.
UTM zone 17 north. And what are the linear units of that projection? Meters. So every cell in our raster is 30 meters by 30 side. And this raster is in that universal transverse Mercator UTM projection. What are the vertical units? What are the minimum and maximum values in that raster?
-79.
So it goes from -79, almost -80 to about 3,500. So what is that, the unit associated with that number? That's what it's describing, but is it feet? Is it meters? Feet. How do you know?
Because that's about the highest point in the state is 3,000.
Right. So
Less.
right. So Sassafras Mountain is about 3,500 feet high. As we look through our properties, do you see anywhere it tells you the unit in that raster? Or is this another Blake trick question for you all? It is. So the raster doesn't care what value that is. It's not assigned through the raster properties. So if we compare our South Carolina DEM, what are the minimum and maximum values there? Especially the maximum. The minimums are not this strange, but our highest value in that is 1,078. So what would that suggest to you in terms of the units of that? That's 1 meters. So our vertical units of our SCDEM are feet. The other one are meters. Okay, so let's compare. Let's take a look at the properties for our South Carolina DEM and just compare what we find in our source tab. So what is our format for this one? For the South Carolina DEM layer. Say it again. FGDBR. File geodatabase raster. So this is a raster stored within a geodatabase. And the pixel type and depth.
Signed integer.
Signed integer. And what's our depth?
16-bit.
16-bit. So this can only store values that are integers. Signed means they could be positive or negative. If you see the word unsigned integer, that means they are positive values only. And this uses 16 bits of memory to store those numbers, so it can store potentially that many values. What else do we need to know? What's our cell size and our coordinate system? 30 meter cell size.
Is state plane?
Is South Carolina state plane?
Yeah.
Right, SC.
It says a linear unit is a meter though.
That's the horizontal unit.
Oh.
So that
Yeah.
means our grid cell is 30 meters. 30 meters. Let's see how you did. Like we nailed it, right? So we missed the datum here, but that's okay. So that's where we can go to learn a lot about a raster data set through the properties. Are there any questions on what any of these things mean?
One's better, the geodatabase. So if it's an integer, I mean, does that mean it tries to extrapolate values?
If you, let's say, run a tool that's going to make a calculation and you store it as an integer, but the result would be some decimal, it will round it. So some tools will output an integer because it might be qualitative or categories, and that's totally acceptable. If you're trying to represent something, say an elevation surface, maybe it's better to have a floating point raster. But one is not inherently better or worse than the other. Other questions? I wanted to show you this because you'll see a lot of these terms out there, and as you explore the data, to download or use for your projects, you might want to be able to identify some of these things. All right. So let's do a few more things. I'm going to close my layer properties, bring ArcMap back, go to my SC bookmark here. So let's open the layer properties for our scdem.tif. The one that's currently turned on here in the data frame. And let's go to the Symbology tab. So one of the most common ways you'll see a raster displayed is what they call a stretched symbology, where it uses a color ramp and then it's going to change the gradation between your minimum and maximum values within that. So you can see all of our beautiful color ramps available to us. I'm going to, for an example, grab this one. Where is it? Elevation 2. And then click apply. There are different ways of displaying rasters, just like we had with our vector data. You can do things like classify the data. So we could use different colors for various ranges of values, and we can classify just like we did with vector data. You can do a unique values. I'm going to not compute unique values because that would take a long time. Where every unique value in a cell would take on a different color. So if your raster is, say, categorical data, you may want to use unique values. Discrete colors or vector fields are other options. So you can display directionality with the vector field. But I'll just apply my stretched color ramp here. And click OK. Some other things I want to point out. Let's right-click on our South Carolina DEM. And notice we can open an attribute table for that raster. And it is docked here at the bottom of my screen. I'll expand it here. And I'll turn on my South Carolina DEM. So what do you see here in the attributes of this data set?
Values.
You see values and a count for every one of those values. So this is what's called a value attribute table, where every record in here represents a unique value in the data set. And then it tells you how many cells have that value. So you can see that there are very few cells overall in our data that are those negative numbers, but then once we get into the positive numbers, I can click on any one of these rows to select it, and I can see which cells take on those values. So if I go to the very high elevations at the bottom of the table, I'm hoping to see that they're more in the upstate. You can query a value attribute table, just like you can query vector attributes. So from my table, I have the select by attributes option here. I'll first clear my selection in the table and then click on select by attributes. So if I wanted to quickly find all those areas here in South Carolina that are above, let's say, 250 meters elevation and below 500 meters elevation, I can just set up a query by double clicking on value greater than, I'll type a space 200 space, click and, double click value less than space, type 500. Click verify to make sure I don't have any errors, click apply. And now I can select those cells in the raster just like I could for a vector data set. Is everybody able to set that selection?
Are you able to export that? Because I know with rasters, like I've only been able to click rasters and you send them.
To just export that subset?
Let's say you're interested in a species that only occurs at that range elevation. Yeah, but you don't want to deal with all the noise that comes from all the other.
Yeah, that's a good question. I don't know that I've tried. I want to come back to that one later, so remind me. During the break, I'll take a look at that one. No, that's great. I'm going to close my selection window here and clear my selection. And then I'll close my attribute table. But let's right click on our scdem.tif layer over here in the table of contents and open that attribute table. There's no option to open an attribute table here because it is a floating point raster. And the number of potential values is so large that, you know, if you have 1.000000, that's different than 1.000001. The number of potential values is so large that the software won't attempt to calculate a value table from it. So it's only integer rasters that will have a value attribute table associated with them. No. Not directly through the table like we could there. Okay. So let's switch back to my presentation here. Any questions, other questions at this point? Everybody feeling pretty good about rasters? Right. And let's talk a little bit about raster analysis and what that looks like. When the software goes to do any sort of calculations on rasters, it performs them on a cell-by-cell basis. And it can look at and calculate several rasters at the same time if they have the same extent and cell size. So in my diagram here, it's not clear what the order of operations is, whether it's, say, adding this blue raster in the middle to the one on the bottom to create the one on top, or subtracting the middle one from the top to create the bottom. You can see here, all of these calculations are performed just cell by cell working through here. So we can do normal math algebra with mathematical functions, logical functions, Boolean, so true, false. You can also apply customized functions to it. Generally speaking, the output of those operations only relies on cells that overlay one another. But there are some families of functions that may analyze a neighborhood of adjacent cells together, and those are called zonal functions. So they use all raster cells, or they are also, sorry, I said that wrong. Focal functions are ones that will apply to some neighborhood of cells. So it will analyze adjacent cells and calculate an output value. Zonal functions are one that look at all of the same cells, or cells with the same value, and analyze those the same way. So as I pointed out before, raster overlay is much faster than vector overlay because we just have these grids of numbers that we're working with. Actually performing overlay may take a variety of different forms, and some of them are equivalent to one another. And what we're going to look at today is reclassifying rasters to perform overlay. So a reclassification is when you simplify the inputs in a data set, say change some set of numbers to another value. And in a site selection analysis, we might want to break it down and say that one data set is suitable or unsuitable, or whatever the purpose is. So anywhere that's suitable gets a 1. Anything unsuitable gets a 0. So if we're analyzing vegetation, we may say that anything that has a value of 2 is suitable. Anything with a 1 or a 3 is unsuitable. We reclassify our rasters so that it becomes 1s for suitable, 0s for unsuitable. And then we can do the same thing with our soils here. So our suitable zone is anything with a 25. Then we can just multiply our two rasters together, and anywhere we have a suitable zone or a 1 in both data sets, our output will be a 1. Anywhere we don't have suitable zones in both data sets will end up being a 0. So a multiplication with rasters that have been reclassified this way is just like saying and, right? I need a condition to be met in both of these rasters. Does that make sense? Questions yet? So this reclassification is a way to simplify our overlay so that we can quickly find suitable zones. So what we're going to do is reclassify a variety of data sets to find where, say, building a big array of photovoltaic cells would be suitable. We're also going to look at some spatial analyst extension tools today. So last week, I showed you where the tools were in the ARC toolbox, and I said that extensions are add-ons to the software, and Spatial Analyst is one that may be of interest to a lot of you. So it has tools and models in a variety of different techniques. Things for calculating density, distance, hydrology and groundwater, interpolation, some of these local and zonal statistics, reclassification, raster calculators, surfacing, solar radiation. We'll take a look at a variety of these next. So the problem we're going to start with our raster overlay is to answer a question: where are the locations in South Carolina best suited for installation of some PV arrays? So somebody's interested in building a large array of photovoltaic cells. Where's the best spot to do that in the state? In this example, best is some area that's barren or lightly developed. So it's not being used for anything useful or has just sparse development on it. It's south facing, so it receives a lot of sunshine, or is flat. If it, say, dips to the north, then that would be unsuitable. We also want it only gently sloping. We're not interested in steep hillsides. So anywhere the ground is flat. So the data we have to look at are those DEMs for South Carolina we've been learning a little bit about. And then that NLCD land use raster. So the National Land Cover Database tells us what each parcel of land is being used for. So we're going to do this using a variety of tools. Our input for a lot of these is going to be that elevation model. So our method is going to calculate the slope from the elevation data. So output a raster that tells you how steep the land surface is, and then also calculate the aspect, which is the compass direction that a piece of land is facing. Then we'll reclassify those rasters to simplify our analysis and use a raster calculator, which is just a calculator for rasters. So you build some map algebra expression, basically like you would type in a calculator for our rasters. So our geoprocessing workflow is going to look something like this. We'll take our South Carolina DEM, run the slope tool, and run the aspect tool and get 2 new data sets. We're going to reclassify our outputs. So anything with a low slope, meaning it was fairly flat, is optimal for us. We're going to reclassify that as a 1. Our steep slopes we're going to reclassify as a 0 because they're unsuitable. We'll do the same thing with our aspect. We'll reclassify, say, if it's south facing, it's a 1. Anything else is 0. We're going to reclassify our NLCD raster and say that barren land is suitable. Anything else is not. And then multiply those 3 data sets together. And anywhere that is a 1 in all of these would be a suitable location. So this is what you could call a Boolean or binary analysis. It tells us only suitable or unsuitable. And it needs all 3 data sets to agree on suitability for it to work. Does that make sense? Questions? So can you see where we're going to go with this, at least conceptually? All right.
These are really helpful. Charts.
Yeah, there's a lot of them in here. Probably too many, but okay. So what we want to do is let's go back to ArcMap. We need to first enable the Spatial Analyst extension. So we're going to use a lot of tools from that extension. We need to turn it on. So to do that, we want to go to the Customize menu, click on Extensions, and then scroll down and check the box next to Spatial Analyst. So you can see there's lots of other potential extensions, but we need Spatial Analyst today. And then I'll click Close. So we're going to use our South Carolina DEM layer as our input for today. So I'll just turn off and minimize my SCDEM data set over here. And now I'm going to search for, starting with the slope tool. So if I hit Control and F on the keyboard, it should open the search window. If it doesn't show up, you can also access it up here at the top. And so we want to start by searching for the slope tool. So I'll type slope, hit enter. And I'm looking for this one, the Slope Spatial Analyst tool. And I'll click on it and open that dialog here. And as I pointed out before, I like to click on the bottom right corner where it says Show Help, because this gives me hints about what I need to input to have the tool run properly. So our input raster here is going to be our South Carolina DEM. I'll click this triangle, select that layer from the data frame. My output raster is going to be saved in the D drive in the Intermediate Spatial Analysis folder in the Results Geodatabase, which is fine. And I'm just going to call this Slope SCDEM.
I'm sorry, I'm behind. How do you find, I'm trying to find the slope tool.
Sure, so I will go back a minute. So I hit Control F on the keyboard to open the search window. No. If you click up here near the top, this little button.
I'm sorry.
It may be showing up in a really weird place.
Okay, yeah, I had to hit this button.
Okay.
My ArcMap keeps freezing up on me.
Oh, let me pass this around before I forget. Okay, so the slope, then I open the Slope Spatial Analyst tool. And so my input raster, I just clicked my drop down and selected the South Carolina DEM. And I'll save the output. The default location should be the Results Geodatabase. And I'll just call it slope _ SC _ DEM. Our output measurement, if I click this drop down, there are two options available to us, whether it's degrees or a % rise. So if you've ever driven on the highway in the mountains and it says 6% grade ahead, that's a % rise. It means it would be dropping 6 feet per 100 feet. Or we could output an angle in degrees. Excuse me. Let's select % rise rather than degrees. We can accept those other defaults and then click OK to run. I'll leave mine up there for a second if you want to check your parameters. So if y'all remember how long it took to buffer some of those data sets last week that had about as many vector entities as there are cells in here, just think about how fast that went. But what it will output for us as it will show lower slopes in green, our highest slopes going up to red. So we're interested in low slopes. Any spots that jump out at you immediately? There's a nice big flat area, right? Too bad it's a lake. But as I zoom in, right, you can see some of these areas in our data set show up as these steeper slopes. And especially as we get towards the upstate, the pattern is pretty dramatic. So here's Table Rock, right? There's the Table Rock Reservoir. If you're familiar with the shape of it, there's Table Rock right there. Did everybody get that data set created? All right, the next one we're going to do is called aspect. So this will output the compass direction. I'm going to search, go back to my search bar, type aspect. We want the aspect spatial analyst tool. And here our input is going to be the South Carolina DEM. And the output, again, I'm going to save in that results geodatabase. I'll call it aspect SCDEM. And we can accept the default settings for the method and click OK. And what you're going to get is a really trippy looking output here that I just like to come in and stare at for on my own sometimes. It's a little incomprehensible if you're zoomed way out, but as you zoom in, what you'll notice is some of these patterns. So the output here, and the legend helps us out here in the table of contents, is that the color is associated with a compass direction. So anything facing north is red, to the northwest is purple, west is blue, and so on. So see along some of these ridge lines, that separation in the aspect with my west facing aspect here, my east and south facing aspect here. So the other thing we need to do is reclassify our NLCD, that National Land Cover Database raster. So I'm going to turn on my NLCD raster and I'm going to drag it and drop it above my other layers here in the table of contents so we can take a look at it. So if you remember the tiger bird problem where we were looking at where the evergreen forest was, this was the source data that helped us find that. So this raster has some code for each one of these cells that indicates what type of land is there, whether it's barren, open water, developed with different levels of intensity, mixed forest, shrub, pasture, and so on. So we need to reclassify all of our data. Let's start with this data set. So we were looking just for barren land. So anywhere in our raster that has that gray color, that's going to be suitable for us. We want to reclassify that with a value of 1, and everything else will be a 0. So let's search for the Reclassify tool. Is everybody with me?
So where did that line come from?
Where did it come from? Meaning, how did it get in the map, or where did I?
Oh, no, how do I like that?
On the machine?
On the machine.
From the ARC catalog. If you go to the home folder at the top, to the data folder, an intermediate spatial analysis geodatabase. There's the NLCD SCSP layer for raster. And it should already be in the map document over in the table of contents. So I'll hit Control F to open my search window. Now I'm going to search for Reclassify. It's the second one in my list from the Spatial Analyst toolset. So here we need to specify our input raster. That'll be that NLCD SCSP layer. And the reclass field, you can see there's different fields in that value attribute table, but we want to make sure we select land cover, because that gives us a nice text field here. So under our reclassification table, we're going to type in under this column that says new values. So we need to go through and change barren land, which is, it wants to assign a value of 6. We need to type a 1. And then we need to go back through and type a 0 for every other category.
What if you have a ton of categories? Is there a
You can, if you work with the same data set over and over again, you can load a classification scheme from a table, which is a nice way of doing it. And you can output or save that classification scheme as well to use on other data. We want to make sure at the bottom, if it says no data, we can leave that as no data. But I'll go back through and check. I have a 1 for barren land, 0s for everything else except my no data fields. I'm going to change the name of my output from their default, and I'm going to call this barren underscore land underscore reclass. And I'll leave mine up on the screen. If yours looks like mine, you can click OK and run that tool.
So if you click save, that would have saved that reclassification.
Yeah, it would save it out to a table for you, and you can load that in and apply it to other data. All right, so I'm going to turn off my NLCD layer to view the output. I'm going to turn off every other one too. So on my map, my barren land shows up with this bright purple, everything else in bright blue. So yours may look a bit different.
Mine's a big fat square. Dang, do something wrong. I put NA values as yeah. Is that you didn't do?
I did not.
That's probably what I wanted.
Underscore at the end of geodatabase rather than backslash it. So what does it look like? How many potential zones do we have already for barren land for developing a PV array? Did it come out right?
Yeah.
Okay. All right, so now we need to reclassify our slope and our aspect. So let's go back to our Reclassify Spatial Analyst tool. In our input raster, let's do the slope. So I'll grab my slope SCDEM layer. And because we have numeric values rather than categorical, we need to specify some sort of classification scheme where it's going to group values together. So we're going to click first on the Classify button, which will bring up this Classify window. And how many classes are we going to have in our output? 2, right? It's either suitable or unsuitable. And so suitable, in this case, is going to be anything with 2% rise or lower. Indicate that it's fairly flat. So first, let's set our classes down from 9 to 2. And then change your classification method to manual. We're going to specify it here. So here on the right where it says break values, we want to change that 11.778 and just click on it and type in 2. And we can leave the other break. That's the upper range of our data. So we have our manual classification, 2 classes. Our break will be at 2. Click OK. And then we need to make sure we set the correct new values. So we want a 1 for any input between 0 and 2, and a 0 for anything from 2 to 375.
Where did we get the 2 again? Or?
I meant to point out before, and I think I skipped it, but this is our what we're considering best.
Okay.
It's flatland, so it's 2% rise or flatter.
Okay.
Yeah, sorry that wasn't clear. I'll change the name of the output here. I'll call it, what do I want to call it? We'll call it slope underscore reclass underscore Boolean. Doing a Boolean analysis here. And then click OK if yours looks like mine. So what jumps right out at you from our slope? At least on my map, I have all these flat areas showing up in bright green. Unfortunately, these are, lakes. But our land cover data will help exclude those, right? Because these are not classified as barren land, they're classified as open land. Everybody there? All right, let's reclassify our third data set then. Open the Spatial Analyst Reclassify. And our input is going to be our aspect input. So if we look through our reclassification table here, the values in our ranges correspond to a particular compass direction. So if you look at the table of contents for the aspect layer, you can see anything that's flat has a value of -1. Anything that's north is 0 to 22.5 and so on. So we want anything flat or south facing. Or actually, in this example, we just want south facing layers. So the south facing values are from 112.5 to 247.5. So if I look in my table, the southeast is this 112.5 to 157.5. I'll keep that as a 1. My 157 to 202, a 1. 202 to 247 as a 1. And everything else is going to become a 0.
What are we starting ones?
It's the one from 112.5 to 157.5. And the last one is the 202 to 247 will be a 1. And we'll call this aspect underscore reclass underscore Boolean. And once you've set that up, go ahead and click OK, run that tool. Click OK. Reclassify. See what we have. So in my map, lots of bright purples that are a 1. These are all of our south-facing areas. So our last step here, we want to use that raster calculator. We're going to multiply these 3 data sets together. So again, anywhere that has a 0 will be output as 0. Anywhere that has a 1 in all 3 of these data sets will output a 1. If it does not have a 1 in every data set, it will be output as unsuitable. So I'll go to my search window and type in the raster calculator, which also comes from the Spatial Analyst tool set. And so from this dialog, we can add rasters from the list on the left and click numbers, values, and other expressions to build that map algebra. So we just want to multiply our reclassified data sets. So I'll double click my aspect reclass Boolean. And then hit the asterisk on my keyboard. So a space asterisk. And my slope reclass Boolean, space asterisk space. And the barren land reclass. And I'll save my output in that results geodatabase, and I'll call it PV underscore suitability underscore Boolean. Then you can click OK. You'll get your output with 0s and 1s. And then you want to inspect that and try to find some areas that are suitable according to our analysis.
Well, 30 meters back, 30 meters here and there.
So I'm going to just quickly add a base map. To help give me some context to the results. ArcMap's going to take a little while to load, apparently.
Which base map did you use?
I grabbed a dark gray canvas. Come on.
Was there a quick fix when it comes up as a square?
Yours came up with just one square?
It's a square, it's got the outline, South Carolina.
Because you changed the NA values of the no data to 0. That's why it goes square.
Oh,
Yeah, okay. So you just leave this in there.
well, that's all right.
Yeah, I get it. That's it.
When we perform our final analysis with the multiplication, those areas would get excluded anyway. Let's see, is this actually going to draw? Not. There we go. So I'm looking for, in my map, these little bits of green. I see a few. Little bits here and there. How's it looking for feasibility of PV energy here in South Carolina according to our analysis? Does it look like it's going to happen? Not enough land? Well, so let me pull my chart back up here. What we've done though is again, our inputs were just elevation and land cover, and through overlay and reclassification, we've output potential PV development areas that are suitable or unsuitable, What about our analysis made us have so few results? Or what's the way we framed our analysis that's so stringent in terms of criteria? It's binary, right? So it's suitable or unsuitable, and it needs to be suitable for all three of our inputs. So this is a very stringent way of framing our analysis. We could try it a different way, though. Do more of an algebraic analysis, where we may have different categories or classes in each one of these inputs. And we may say that one is more favorable than another. So if we look back at our slopes, anything that's flat is most desirable. Let's give that a 2. A moderate slope is a 1. Anything that's too steep would stay a 0. Reclassify again, anything south facing is most desirable. Anything flat is good too. Everything else, a none. Here, maybe barren land or lightly developed areas are okay. So we can rank those accordingly. And then rather than multiply, we could just add up those values. And then our output is going to be some ranking from 0 to 6. And we can evaluate better and worse a little better than just yes or no. So here I've gone and just made up some classification scheme, but this process is something you would often do in a site suitability analysis. So let's go for it. Let's try. Redo our reclassification methods here. I'll just start minimizing a few things in my table of contents. Just to save the time in redrawing them every time. But let's reclassify our data just like we did before, but now try this algebraic overlay method. So I'll go to my search window, search for the Reclassify tool from the Spatial Analyst tool set. And we'll start with that slope raster again. So my input, I'm going to grab my slope SCDEM. my reclassification is going to be excuse me. I need to click my classify button. We're again going to do a manual classification, but with 3 classes. So I'll change my number of classes to 3, my method to be manual. I'll keep that first break value as 2, and then the next one as 4. So it should say 2, 4, and then 375 dot whatever. So that 2% slopes and under are going to be our highest, most suitable class. Between 2 and 4, acceptable. And anything higher than that, we want to give a 0. So I'll click OK. And then change those values where 0 to 2, let's give that a new value of 2. 2 to 4, a new value of 1. And 4 to 375, a value of 0. And no data will leave as no data. And I'm going to change my output. I'll call this slope underscore reclass underscore algebraic to differentiate it. And then once you've set that up, you can click OK, run that tool. So here in the results, I can see a change, right? Where now these flat areas, again, our lakes are going to show up in bright green. But then I also have these purple areas that are a bit steeper and were excluded from our initial analysis. So already we've opened up a lot of different potential options for our photovoltaic arrays. Everybody with me? All right, so let's reclassify our next data set. Go to our aspect. Reclassify from Spatial Analyst. Set our input raster to the aspect SCDEM. And here we're going to put a 2 in next to the 112.5 to 157.5 through to the 202.5 to 247.5. Our first row where it says -1 to -0.001 will leave with a new value of 1 and change all the others to 0. That first row indicates that it's flat. And I'll save my output as aspect underscore reclass underscore algebraic. And once you've done that, you can run that tool. So now I see all these flat areas show up in purple on my map. Bright green is south facing and anything else is in a dark green. All right, last data set we want to reclassify. I'll open my tool once again. Go back to our land cover. So our input will be our NLCD SCSP layer, the National Land Cover Database. And we're going to give barren land a value of 2, lightly developed a value of 1, or developed low intensity value of 1, and everything else is 0.
What is it? Low intensity development is 1?
Right.
And then everything else is 0.
And barren land was a 2.
Yeah.
Yep, and everything else is 0, leaving no data as no data.
Why would developed open space not be one?
Oh, thank you, Charlotte. Developed open space. That's the one I wanted. As a 1, low intensity is 0. Didn't see
Low
that.
intensity is 0.
Right. Yep, so developed open space will give a value of 1. Developed low intensity is 0. Sorry about that. We'll save this. Excuse me. Give it a new name, call it a barren low intensity reclass. You can run that tool, and once that finishes, we'll run our Raster Calculator. All right, so next, search for my Raster Calculator tool. From the Spatial Analyst toolbox, and I can double click my layers and set my expression. So here I'm going to multiply my barren low intensity reclass times my aspect reclass algebraic. Oops, I didn't mean multiply, I meant plus. So it's barren low intensity reclass plus aspect reclass algebraic plus slope reclass algebraic. And I'll save my output as PV suitability algebraic. You can run the tool and view the results and then compare them to what we saw just a couple minutes ago from our other analysis.
Like I had to sit down and redo everything. So what were the on the classification or slope? What were the
3 classes.
so go back to the grades. Or and then keep that.
And then 0 to 2 is 2.
And then for the aspect reclassify.
That was flat, which is the first row is a 1. And we put a 2 for the 100 as well. 7, 0.
So all of the slope sets.
Just so I'm clear on this, so when we were doing the Boolean, Raster Calculator Boolean, you used, you multiply it,
Yes.
and then for algebraic.
We're adding. Yeah. So, yeah, before when we had the Boolean, all of our input reclassified rasters were either 1s or 0s. So if we have 2 rasters, you know, with a 1 and a 0 and a 1 and a 1 that overlay each other, if we multiply these, then our output will be 1 here and a 0 here. Which is the equivalent to saying and. Here, we have more of an or statement where we're going to add up the rasters use different values, say 0 to 2, to weight these differently. So this is a weighted overlay. So things that are more suitable in our analysis were given a higher value or are deemed more important than others.
Did you multiply or add them?
I added them up.
Oh, why did you multiply?
So if we multiply, then anywhere we have a 0 is going to come out as 0, regardless of what overlays. Here we have different grades of suitability. So my output has values of 1 or 0 through 6.
But if hypothetically you didn't want any, you wanted all the criteria to be met.
You want all the criteria to be met, right? So anywhere that's a 4, 5, or 6 means that it has at least a 1. So some suitability. Anything from 0, or I should say 3 up through 6. Anything 0, 1, 2 means that it was unsuitable. And at least some of these data sets.
But I feel like I got the same results probably.
I wouldn't think so. Because anywhere that's a 0 in any of those data sets would still come out 0. So you're excluding potential areas.
But I want to do that, because you're saying right now, don't consider anything from 0 to 3.
I'm saying that this is the output of those. It's saying that this would be suitable in all of those. I'm not saying exclude these completely. But it could come down to, well, I didn't find anything totally suitable if I ignore slope, for instance. What are some potential zones? So here there's just much more nuance to the output. Again, my weighting criteria is totally artificial. I made it up for this example, but great questions. So what did you find? Any areas where we can go build our PV cells? I might change my symbology here. So I'll open the layer properties for the output, my PV suitability algebraic. Go to my Symbology tab, and I'm going to do unique values, but I may want to do something that use a gradational color ramp rather than a categorical one. So if I right click on my color scheme, will it let me uncheck graphic view? I'm going to find the one called Spectrum Full Bright. Somewhere in here. Spectrum. There it is. Spectrum Full Bright. And I'm going to right click on that word symbol. Nope, it's not going to let me. I'll just click on that word symbol and click flip colors. So that I would have cool colors indicating low suitability, warmer colors indicating higher suitability. Click apply. Click OK. I'm going to turn off some of my other data sets here. I'm additionally going to go to my 0 from my table of contents, click that box next to the number 0, set the fill color to no color, click OK. Whoops, I don't think it took. Fill color, no color, click OK. So any areas that look especially promising? I can also grab that value attribute table, say select values of 4, 5, and 6. Maybe that won't help because I have so many blues in the map. We can also customize our symbology a bit further. Close my attribute table here, double click the layer from the table of contents, go back to my layer properties in the Symbology tab. Let's group together some of these categories and symbolize them the same way. So 6 we'll leave on its own, but if I click here on the 3 and then hold shift and click on 5, or 3, 4, 5 to select all 3 of those, I can right click and select group values. And then I can symbolize all of those the same way. And I'll do the same for 0, 1, and 2. Click on 0, hold shift, click on 2, right click, select group values. And I want those to be no color, so I don't even see them in the map. Then I can click OK. Turn my base map on again. Now I can see the zones that have at least some suitability. Whoops. That had a 1 in all 3 of my data sets, and potentially any very suitable zones, which are kind of few and far between, as we saw in our last analysis. There's one. One raster cell. There's a 900 square meters of space we could cram some solar cells, right? Questions on that analysis? Does it make sense what we've just been doing in these 2 different approaches? So first, we took this Boolean or binary analysis where we weighted everything as suitable or non-suitable, and then did an algebraic or weighted analysis where now we have a score where we can compare one location to another. And so our output here looks something like this. Questions, comments? Let's take before we go to a break, I know we have lots of time left, but some of the other examples I have for today would be to delineate watersheds or catchment areas using an elevation data set. So I have points that mark the location of the USGS stream gauges. These measure flow in a river and other parameters. You can delineate the area that drains to a particular stream gauge or the watershed using specialized tools. I have an example of creating contour lines from rasters. So if you're interested in contour lines to show topography and how to get those, say, from an elevation data set, I have an example of those, and then some examples of interpolation. Interpolation is where you are going to estimate unknown values between sampling points. So if you have sparse sampling locations, you're going to estimate values between them using some sort of interpolation method. And so use a few different interpolation schemes to estimate temperature distributions over South Carolina. Because some of these are a little longer than others, how many of you are interested in the watershed delineation? I think that would be useful. We got one strongly, and those watching remotely can vote too as well. How many want to see for sure how to generate contour lines from elevation data? One, okay. How many would be interested in interpolation, so estimating values between data? And you can vote for more than one. So I'll go through one more time. I'll go back through. Okay, watershed. 1, 2, 3, 4, 5. Contour lines. 2, 3. Interpolation. 1, 2, 3, 4, 5, 6. Okay. We may be able to get through all three of them if we go quickly, but let's take a break for about 10 minutes. Stretch your legs, grab some water. The contour line ones is very quick. We can cover that regardless. I'll see if we can get through all three of these. So we'll meet back at 40 after. Thank you.
So it could be hopefully a really quick question if you've got a minute.
Sure.
I was trying to get a shapefile for
right. Still waiting on a couple people.
First time we did movie. So, three times, we added numbers. That's how we got this.
I just want to let you know that I'm picking up my friend at the airport in Atlanta at 7:30, so I know we didn't leave a little bit before, but I just didn't want to feel like I was being offensive. So I think that was-
All right.
What's your email?
BALYTL.
Yeah, they'll want to.
Right. All right. So the next thing we're going to do is we're going to continue using some spatial analyst tool sets. And so we're going to delineate watersheds, also called drainage basins or catchment basins. And so the watershed is the geographic area that drains to a particular point. So these are areas where any precipitation that falls would end up in a stream within that area. So from my picture here, this white line separates areas within the basin from without. So at the edge, we have these drainage divides that function a lot like a roof. So water falling on one side of a roof will drain off in one direction, water falling on the other side of that roof drains off in the opposite direction. Here within the watershed, or at the divide of our watershed, this white line, here we're separating flow. So anything that lands as precipitation inside this boundary will end up in streams that all join together and flow out down to this lake down here. In the terminology of the GIS, we have something called a pour point. And the pour point is a location for which we're going to determine that drainage basin. So in this picture, my pour point would be down here near this lake. So what we're going to do is look at some USGS stream gauges and determine the catchment basins or watersheds for those. So there's several tools we're going to link together to do this. Our input is going to be our digital elevation model. The first thing we need to do is use the fill tool. This will fill in any closed depressions in the data set. If you think of a road and a pothole in the road, a pothole is essentially a closed depression. Everything would flow down into it without leaving. We want to fill those in because they make it tougher to delineate basins accurately. We'll then do a flow direction tool, which is a lot like the aspect tool, which showed us which way an area was facing. This points, say it again, this will output the direction that's downhill or downstream within the raster. So it works a lot like our slope and aspect tool, but will output flow directions, or which direction is steepest from one cell to another. We then run a flow accumulation tool that reads through and counts how many cells in that flow direction output are downstream of one another. And anywhere that has a large number of cells downstream of it is where it's going to be high accumulation. Basically, that means a high likelihood that a stream would be located there. We're then going to snap or adjust the locations of our pour points to zones of high accumulation in our input. Just a small adjustment, and then use the watershed tool, which goes and delineates those basins, separates them from one another. So here on the right, you can see these tiny blue triangles. Those are my pour points, and the different colored regions are the watersheds or areas that drain to each one of those points. Finally, we can do things like run our zonal statistics on that. So a zonal statistic is one that calculates some property for all cells that have the same value. So we could take our slope raster, we could calculate or average the slope in each one of these watershed boundaries to determine if, say, one particular watershed is much steeper on average than another, which is important to various hydrologic forecasting models. Questions? Does everybody kind of see where we're going? I know this is not in everybody's background and it's a lot of tools here, but so this is what we'll do, what our workflow is going to look like. We'll start with that South Carolina DEM once again, run the fill tool, the flow direction tool, and flow accumulation tools. We'll take our stream gauge, which are a set of points. We're going to snap those locations to high accumulation zone. And those two inputs will be put in the watershed tool, which will output these watershed areas. And then we can run zonal statistics on the watersheds to determine their average slope. So there's our flow chart. And so this analysis question we would be answering is, what is the average slope of each watershed in each basin associated with each one of these stream gauges? So let's give it a try. So I'm going to minimize my DEM's data frame over here on the left. I'll expand my watershed delineation data frame and then right click on it and click on activate. So what's already showing in the map, these are the locations of my stream gauges, these blue triangles. So I'll click my identify tool and just click on a few of these to learn a bit about it. They have some IDs, they have some codes. I can see when it was installed and so on. But each one of these is installed in a river, and it tells you the volume of water flowing through it, as well as potentially some other factors about the water. Sorry, I'm being told they can't hear me. Is it just UPO, or can anybody else not hear me? I know I'm unmuted and some people are able to hear me. I may have to continue. If multiple people can't hear me, I may leave the room quickly and come back. All right, so what we have here are our USGS stream gauges. We also have this SC upstate DEM, so a digital elevation model that's been clipped to a portion of the state. So what we want to do is first run the fill tool, which is going to fix any imperfections in our data model, fill in those closed depressions. So here I'm going to hit Control F on my keyboard to open my search window. I'm going to type fill, F-I-L-L. And we want this fill spatial analyst tool. And we just need to specify our inputs and outputs. So our input will be our SC upstate DEM. I'll save my output in the results geodatabase, and I'll call it filled DEM, F-I-L-L, whoops, F-I-L-L underscore DEM. Click OK, run our tool. To run this one before we took a coffee break, right?
I can't seem to load the stream gauges. Not showing up on the map.
Oh, yeah. You just need to activate it.
Any minute now, tool. I haven't run this one lately. I kind of forgot how long it took. Did anybody's finish yet? No. It's not just me. All right.
Do you put a Z limit on it?
Nope.
So did we have gaps in the data that we needed to use?
What it's going to do is just look for anywhere there would be a zone of cells that have flow coming into it and not out from it. And it basically fills that in, makes it flat. Because for the delineation or flow accumulation to work, it needs a linear path that continues through the data. And those would suggest that there is a divide in drainage, that there's flow going in and not coming out. And it would interfere with our calculation.
So essentially because the resolutions are square, is that?
No, it's just assuming that areas that are closed depressions are, it's not assuming, but for the calculation method and tracking flow, it needs to not have flow that stops. It needs to continue on to some point and accumulate. And those would suggest a divide where there isn't one. Maybe I'm not explaining it super well, but we just need to fill in those closed depressions.
Your values kind of different.
Hmm?
Your value It's different from what we have. The high and low one.
You have higher and lower ones? Do I? Yours looks good. Yours looks good. Mine doesn't. Everybody got something different? Awesome. Well, I'm going to continue on, and your final results will look slightly different from mine. But you should use your fill DEM in the next calculation step. So we want to now search for flow accumulation. And from our Spatial Analyst tool set, flow accumulation. So you'll set your input flow direction raster as fill. I'm just going to use my DEM so I don't have to wait for that again. And I'll save my output in the results geodatabase and just call it flow underscore accumulation. And I'm going to set my input or my output data type to an integer rather than a float. Click OK and run the tool. Yeah, I'm not sure what happened in my calculation. It got some crazy elevations from negative infinity to infinity just about. And you will probably get something very different from me for your flow accumulation. I'll see you afterwards. There you go.
I'm good to 21.
21.
Yeah.
Interesting.
Yeah, mine too. And everything was big fat zero.
Let me view my output here. Yeah, something's not right. Oh, I skipped a step, everyone. Sorry. Let's first go to flow direction. Search for that tool. Let's skip this step. It's easy to do when we have so many. So what I meant was for the flow direction, and this will run on your filled DEM. So our input surface raster for this tool is our filled DEM. I'll run it on my upstate DEM. And our output, I'll just call flow direction and save it in my results geodatabase. So once I have my flow direction, I should have another very colorful data set, and my flow direction will be input into the flow accumulation.
Sorry, what was the input for flow direction?
The input will be your filled DEM. Okay, so I will remove my old flow accumulation from the data frame. I'll right-click flow accumulation and remove it. Here's my flow direction. And now I'm going to run my flow accumulation tool. search for and open. So I need to specify my flow direction as my input. And my output I'll call flow underscore accumulation. And because it doesn't like to let me overwrite my output, I'll call it _2. And again, I'm going to set my output data type to integer and then click OK. Okay, so here's our flow accumulation data. You zoom in, the lighter colored cells are cells that have lots of upstream or uphill cells in that elevation data set. So anywhere that shows up with a lighter color is a likely location for a stream. We can change our symbology a bit. I'll open my layer properties. By double clicking the layer, go to Symbology, and I'm going to set it to classified with 2 classes. And then I'll click the Classify button and set my lower break to 250 or 300. Click OK. Click Apply. And this is more of just a visualization thing here. I may need to change my break value lower and lower, maybe 100. Maybe even lower. And what I should see is that they all start connecting, these zones of accumulation, and begin to look like streams. So you kind of have to find the magic number in your data that connects all of them. Does yours look similar to mine or a little different?
Still running.
I'm still running.
Still running, oh. Okay. Then I will pause for a minute. The visualization isn't as important. Just let me know once yours have finished. I'll keep playing with mine here. I have a feeling mine is not going to work properly. So what our next tool is going to do, we need to snap our pour points, which means that we need to adjust the location of these pour points and move them to a cell with a high accumulation value. Which one? The symbology? Sure. So I opened my flow accumulation output, layer properties, went to the symbology tab and changed it to classified with 2 classes. And then I've been playing with this value. I need to set mine pretty low. And judging by my output, I'm going to have some very bad results. I see somebody else's.
Ours is just black.
Mine's at 50. Should I change it to 2?
Yeah, yours is a little better than mine. Because I didn't fill the raster.
Yeah, I got.
Yeah, this one looks good. So you see how all these lines connect and kind of look like streams? Which number? 30. So mine's gonna have problems, I think, because I didn't get a good fill result. But we'll continue on. So what we want to do again is we're going to move our pour points to a cell of high accumulation. We basically need to force them onto a stream so that when we trace upstream in our tool, the calculation will work. So the next tool we'll run is called the snap pour point. And there's only one of those from our Spatial Analyst tool set. So our first thing that we need is our pour point data set. And so that it's our USGS stream gauges. Our input accumulation raster will be that flow accumulation 2. Our pour point field we can just leave as the object ID. We'll save our output as USGS underscore snapped underscore gauges. And our snap distance, this is how far we will allow these to move to get to a cell of higher accumulation. And we can try 150, which means we'll allow these to move up to 150 meters. And once you've set those, you can click OK, run the tool. And so what you'll see in the output is a new raster data set where the cell of each one of these gauges, once it loads again, has been moved slightly relative to its location in the vector data set. So it's moved it to higher accumulation, which is important for our next step. Is everybody there? Anybody still processing? Need to wait?
My values though for the snap gauges look much different.
The actual numbers here?
Yes.
That's okay. You may have selected a different field. It's just an ID for them.
Oh.
That's okay. So the next thing we want to do is search for the watershed tool. Somewhere down here, watershed spatial analyst. And so this needs a flow direction raster. So that's going to be our flow direction. And our input raster or feature pour point data, we're going to use those snapped gauges, that one we just created. So our USGS snapped gauges. Our pour point value field, we can leave that as value. And we'll save our output raster and just call it watersheds. And once you've set those, click OK, run the tool. I'm interested to see how mine looks. I think you guys should get good results.
It actually is a coincidence.
Really?
Yeah.
So I got a very, very bad result. it's showing them as being way too small. Did it work for anybody else? Good. That's good. 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 I wish I could show one of your screens up here. In the interest of time, I won't go back and rerun all of these, but what you should get is something like this, right? So each one of those colors is associated with now a boundary for all of these different watersheds, or the areas that would drain to one stream gauge and not another. So pretty neat, huh? And actually, if you drag, let's see. Oh, what you can try is turn on this layer, the WBD watershed boundaries. These are from the National Hydrographic Data Set. These are, I'll put in quotes, official watershed boundaries. Compare those to what you just output with the tool. And unfortunately, mine didn't work so well, but I think for a lot of you, you're going to find they're very, very, very similar. The bookmarks menu, I'm like, that's fun. What's that number?
Yeah, what are these?
So the numbers for each watershed, this was, the number it assigns was when we ran the tool, it gave us, it asked for the pour point field,
Okay.
which is going to be a code it reads in and applies to the output. So I just used value. Whoops, from my.
We can't necessarily discern anything from that.
No, it's more or less an arbitrary number, right?
Oh.
But now I see my watershed that has the code 1 corresponds to the pour point with the code 1. So if you had, say, station IDs or sensor IDs or something, you could use that as input to the watershed tool and then link those two through a common code. Any other questions?
In some areas, if we don't have the relating of the base, how can we use the ones?
If you don't have these gauges?
Yes.
Okay, so this particular workflow is for when you're trying to delineate the drainage area to a specific point. So here, our points of interest are these USGS stream gauges. For some other people, they may have a sensor in a river and they want to characterize the area that drains to it. So those would be their pour points. There's also the basin tool. If you just search for basin, this will delineate all the drainage basins in an elevation data set. So if you're not interested in calculating the watershed to a point, but rather finding all the basins in the data set, that's another way of doing it.
And the raster you would use for that would be.
You'd still run a fill DEM. All right. My background's in hydrology, so I thought this one was really neat. Hopefully some of you will find this useful in your research or projects. But what it does is it, again, gives you some exposure to the Spatial Analyst toolset, an example of geoprocessing using here, all we had was an elevation data set and some points, and we're able to calculate those drainage areas to it. In the interest of time, we'll skip the slope calculation part and go to our next one, creating contour lines. So contour lines are these lines that connect points of equal elevation if we're talking about topography. So in many instances, you don't want, say, an elevation raster. You'd like, say, lines that represent topography for analyzing other tools, or even as an input in your map. It may be more appealing or more intuitive to show topography using lines here. So the Spatial Analyst contour tool will generate these for you. You tell it the contour interval, or the gap between contours, the starting contour value, and then a Z factor. So if you have an elevation data set in meters and you'd like to output contours in feet, you can scale it and output it directly. We'll do this twice to show how the resolution of input data makes a big difference on the quality of your contour lines. So we'll use first a 30-meter DEM that's been clipped to the Clemson area right here around campus, and generate 5-meter contour lines. And then we're going to use an elevation data set that was derived from LiDAR data, or these point cloud data, that has a 2-meter resolution, just to compare the two. So I'll switch back my arc map, and I'm going to activate my creating contours data frame. So minimize my watershed delineation data frame. Right click on creating contours, click activate, and then expand my data frame. So here we have currently showing the campus boundary shown in purple for reference. So we're, I don't know, right about here, the center of the map. And we're going to create some contour lines from this elevation data set. So this one is our 30-meter resolution data, which is a typical product you would find, say, from the USGS or other portals. So let's start by creating contours from that. I'll search for the contour tool. Again, from our Spatial Analyst tool set. We'll click contour, set my input as this SC upstate DEM. I'll save my output. It's going to be a line data set, right? So a vector data set as lines. And I'll call this contours underscore 5M. We're going to do 5-meter intervals. And I'll call this underscore upstate DEM to differentiate it from the other one we'll create. Our contour interval will be 5. We want it to be every 5 meters. We can specify a base contour, or the contour we want to start from, or let it select for us, which we'll do. And then click OK and run the tool. So here's our output. And if you open the attribute table for those contours, you'll see it gives you, in the contour field, the actual value of the elevation. So these are elevations in meters. If you wanted to, say, make a site map, I'll zoom in a bit, and you wanted to label the elevations of those contours, you could label the features, go to your layer properties, and set your label to the contour field. And if you then turn off that DEM, you can see here's my elevation. My labels get a bit blurry here. I'll turn those off. So how do these look? What do you think? Does it look about right?
You click label features. Sorry, what did you, in the labels tab you click what?
I set my label field to contour. So what I notice are, there are some interesting features. There looks like a hill or something. I'll switch my DEM back on. I guess this is actually a little basin right here. I see another hole right there. That's probably the stadium. Kind of interesting. So this was our output with our 30-meter data set. So I'm going to switch off my upstate DEM and switch on this one called Clemson LAS to DEM. So here's a 2-meter resolution data set derived from some aerial LiDAR data. So I think already you can see a difference in the input data. All these areas with creeks on campus show up. I can very clearly see the stadium in our input data. So let's go back to our contour tool and try again. We'll set our input raster to now that Clemson LAS to DEM. Save my output contours 5-meter underscore LAS to DEM. I'll set that same contour interval of 5 and then click OK and run the tool.
Is that data set just a raster with like a smooth gradient applied to it?
No, they're 2 elevation rasters. It's just that on this one we have a 30-meter cell size, and on this one we have a 2-meter cell size. Yeah. Yep. So the difference in the contour lines is pretty dramatic. And so this looks much like I would expect if I turn off my DEMs. Turn back off. There we go. Here I have some very nice clean contour lines. And I can even make out features like some of these aquaculture ponds out here. I can see the dikes very clearly up near Lake Hartwell. But here the contour tool allows us to convert some sort of surface into a line data set. How hard was that? Scale of 1 to 10. Super easy. That's okay. What was your question?
I was just wondering whether, like, this is just line data, and you might be interested. I was thinking, like, you might be interested in vectorizing that, so it's like polygons instead of lines, but then you just use the reclassification tool for raster.
Yeah, you could go that way.
I just don't think that.
Okay. Any questions on the contour lines and any other questions? No. All right. So then the final thing I want to show you all is how to do some interpolation in a GIS. And so interpolation is some sort of function that you would use to estimate values in between your data. So if you go out in the field and say I have a bunch of instruments that measure temperature, you know what the temperature is at those weather stations, but you don't know what they are in between. But if you know, say, a set of temperatures, you can interpolate or guess in a rigorous and standardized way what the values are in between your stations here. Interpolating in GIS is something that's very easy to do, and as such, it's something that's very easy to misuse or to use incorrectly. So If you're going to go this route and want to perform interpolation, it requires a fairly in-depth understanding of your data. So knowing the statistical distribution, if it's symmetric, if it's normal. Do you understand the covariance relationship? So do values vary together across space, or are they totally random? And what is the covariance between your values, as well as relationships between how similar adjacent features are or dissimilar to features far away? So what is a relationship between distance and variability in your data? You also need to know assumptions of the interpolation scheme, because depending on the method, it may require certain things to be true in your data, such as, is it normally distributed would be one, but also, is the mean stationary, or does the average of your data vary over space? What is the distribution of your population, right? So is it normally distributed? Is it skewed in any way? And are there overall trends in your data? Say, if we go back to our temperature example, we know temperature tends to increase as you head south, right? As it gets warmer. So are there trends within your data? These are all things you need to know or be able to find out about your data to understand if you can interpolate them with these different methods. So what I'll show today are what are called deterministic interpolators. And these use either some mathematical formula that's fairly simple or just uses neighboring values in their relationships. And they don't assume much about your data and are therefore fairly safe to use, but they may not give you very good results. And we'll take a look at some of these. We'll use the trend tool, which fits in a least squares sense a surface through all your points. And so if you want to find, say, a general trend in your data, if it increases or decreases in some direction, this is a way to do that. It's inexact, meaning that it rarely ever fits the actual values of your data. It's not trying to. If you imagine a two-dimensional trend line with a scattering of points, it generally fits through the center or the mean, but not any point in particular. So the trend tool is good for doing just that, finding trends in the data. We'll also look at what's called inverse distance weighting, or the IDW scheme. And so what this does is it uses points adjacent to a location and takes some average of those points. And it weights things that are near to one another more strongly than those that are far away. So the weighting is an inverse of distance. Basically, what it's assuming is things that are near one another are more similar than those that are far away. Or, as I've said here, greater distance means less influence. So what this will do is lay some grid over your sampling points, and then for each cell, it's going to take a weighted average of all your data. And it's going to weight most heavily those points closest to it. Spline is another deterministic interpolator here, and this is going to fit a surface once again, but it's going to do so in a way that minimizes curvature. So it makes a very smooth output. And you can do things like output a regularized spline, which tries to minimize curvature in the first, second, and third derivatives. And then you can also have a tension spline, which is one that uses more of your data and has a smoother output, but takes longer to process. So we're going to look at the trend, IDW, and the spline values or methods today. Any questions on those? I have a couple more points I want to make. How many of you have heard of kriging before? Anyone? No? Okay. This is a tool that's very easy to access in GIS. It is a powerful interpolation scheme. It's similar to our inverse distance weighting in that it assumes things that are close to one another are going to have more similar values than those that are further away. But what it also does is it models variability as a function of distance from your points through something they call the variogram, where it fits a model of covariance as a function of separation between points. And this requires an in-depth statistical analysis of your data to fit that semi-variogram model correctly. There's different flavors of kriging that assume different things about your data, such as the mean does not vary through space. Ordinary kriging can account for linear trends or a mean that's non-uniform. You can also do co-kriging, which is where you take multiple data sets together to help inform your interpolation. And so these are all easy to do in GIS, but without understanding what you're putting into that model, you will not be able to trust your results. And so this is a tool that's very often abused. So I would say, don't do it unless you know what you're getting into, especially if you're going to present those results to, say, your dissertation committee or try to get them published. It's easy to make a nice looking map or result with kriging, but if you don't understand your data on the operator, your results are not going to be valid or reliable. In the next week's workshop, we're going to look at a bit more on statistics and spatial statistics, things like spatial regression, look at autocorrelation and how we can use that to find statistically significant clustering of data, which they call hotspots. If you'd like to learn more about kriging, you can take a course called Geostatistics in the EES department. You'll do kriging for half a semester at least. Esri eLearning, which you all have access to, has some other options and show you more about the Esri Geostatistical Analyst tool set if you'd like to learn more. So what we're going to do before I spoil the results is take a look at some temperature data for South Carolina. So I'll go back to ArcMap here. We're going to interpolate values across the state. I'll minimize my creating contours data frame, right click and activate the interpolation data frame. So what we have here are temperatures in South Carolina from all of these weather stations from September 2016. And if I right click and open the attribute table, I have a station ID, and this T average is that average temperature in degrees Fahrenheit for the month of September 2016. So what we want to do is try to estimate average temperatures everywhere in South Carolina, and we can do that by interpolating. So what we'll do first is this trend tool. So I'll go to my search window and type trend for my spatial analyst tool set. So my inputs to this are going to be point features. It's going to output a raster. So my input point features are going to be that SC temperature data set. The Z value field is the attribute you're trying to estimate. So here it's at T average. And our output raster will save in our results geodatabase. And I'll call it temperature underscore trend. And I'll just accept the other defaults here. We're going to perform a linear regression, find a linear trend. So before I run the tool, what will we expect it to look like? Hotter towards the coast. That's what I would say. Everyone agree? Sounds reasonable. Let's see what the data have to say about it. Let's click OK. Run our tool. So here in the output, cooler temperatures show up in green, going through yellow, red, all the way up to white being the warmest. So which way is our trend of increasing temperature? To the south. To the southwest a little, east a little bit rather. So yeah, towards the coast and to the south. What I want you to do though is, did I bookmark Clemson? Go to your bookmarks menu, click on Clemson. And I want to compare, can't find my temperature station. There it is. You may have to zoom out a bit, but here's a temperature station. Let's identify it. Click the identify tool, click on the point. And what was the average temperature at that station? 67.16 degrees. If you click then and identify in the raster, oops, I need to change my identify from and select my temperature trend and then click again. And just start clicking a few cells around that temperature station. So what did it estimate the temperature to be? 64 point something. So it underestimated by something around 3 degrees. So just keep that in mind. I'll go back to my bookmarks menu, select SC, and zoom back out. So the next interpolation method we'll try is IDW, or that inverse distance weighting. So if you type IDW and search for it, we'll grab that IDW from our Spatial Analyst tool set. And our input point features will be our temperature data. Our Z value field will again be T average. And we'll save the output in results geodatabase and call it temperature IDW. Temperature underscore IDW. And we'll accept all the other defaults. The power here is the exponent in that inverse relationship. So it's going to fall off as 1 over the distance squared. I'll click OK. IDW. And now I have a result where I see more information, right? So I can see clusters of higher and lower data, higher and lower temperatures, especially here. I don't know what they call this part of the state. South Carolina people, help me out. Oh, what? Is that the PD area? Okay, thank you. I'm not from here originally, so I'm still learning. So in the PD area, we had one station that looks like it was much colder than the one nearby. And if I identify, whoops, identifying from the wrong data set here. I see my actual temperature data. That location was almost 71 degrees, and over here was 53 degrees, so a huge difference. But let's go back to our Clemson bookmark, find that weather station again, and then compare the results. So I grab my identify tool. I want to identify now from my IDW data set. What does it estimate? Like, I get around 67.1. So it's within 0.3 of a degree overall. So because it's taking some weighted average of the surroundings, we get something that's much closer to our actual data. What you often see in IDW, they call these bullseyes, right? Because it's just taking a linear average around this weather station here, you can see it's going to have these rings around it. So you see these bullseyes around individual data points. And then in between values, it trends towards the mean of the data set. So let's try our third option then. Let's try the spline and see what that looks like. So I'll search in my tools for the spline in the Spatial Analyst tool set. My input features will be that SC temperature. My Z value field T average, and my output I'll save as temperature underscore spline. I'll accept the other defaults, click OK, and run. That looks different than I expected. That's all right. So here, again, what this is trying to do is fit the smoothest surface through the data as possible. So we still have these localized areas, but we don't have that dramatic bullseye effect like we did with the IDW. So let's compare this one to that Clemson weather station. So I'll identify from my temperature spline. And I get things right around 67 degrees. So again, it's not exact, but fairly close. So which one is right? Any thoughts?
Who knows?
Who knows, right? We just made it up. That's all interpolation is, but it's a rigorous way of estimating values, right? So this is a way you can take sparse sample data and try to estimate what's in the gaps.
I feel like that 53 degrees is a fluke, so I feel like the first one is the best.
You think the trend?
Yeah, because the other ones highlight that so much when like something was wrong. There's no way that was that cool there and warm everywhere else around it.
Let's see, which data set was that? Yeah, that's a good point. Can you actually trust your input data to be accurate? I'm just wondering if there's anything locally around there that would suggest why it'd be so much colder. Maybe it was near a lake. That doesn't seem to be the case for us, though. So what I'll point out, though, is that at least with the IDW, the weight that it's going to use to average out this station for one that's far away is going to be minuscule. So it has a very strong impact locally, but over here, the impact of that point is negligible. Yeah, good point. Any other questions on interpolation, comments?
Can you explain the difference?
The difference in the method or in the result? Sure. So our first one, we fit a trend. Basically, we fit, in a least square sense, one surface through the data, and that shows us the overall direction from high to low. And so for us, lower temperatures were in the northwest, increasing to the southeast. But what it doesn't show very, very well are regional fluctuations within the data. So our IDW is going to, for every point, take some average of all your data points, but it's going to weight most heavily those that are nearest to it. So that's why around this station, it gets very, very low right next door, but then as you get further away, the influence is less and less. So here we can see the influence of individual weather stations more clearly. With our spline, we're trying to fit a smooth surface through it. So if you imagine, how do they describe it? If you're trying to fit like a rubber surface on a bunch of pointy objects that's as smooth as possible, it's something to that effect here. So here we have something that's very smooth, but kind of smooth without variability that we may have, like you could see with IDW. So if smoothness is important in your output, this is a good way to go. I would most commonly see people using IDW. Does that make sense? Other questions? Great. So that's all I have for you today. If you could please fill out the survey at this link. That would be great. Enjoy your weekend. Like I said, next workshop, I think they're both on Friday. From here on out. Let me double check. Well, no, I take that back. It's Friday and the following Thursday. It's the next one that starts to be back-to-back on Fridays again. But the next session is going to be an introduction to spatial statistics. So how do you fit trends through your data, identify clusters or hotspots, and spatial autocorrelation, as well as spatial regression. So doing things like fitting a trend through your data, but now instead of points in a 2D plane, let's say you have county population data or some incidence of cancer at the census block group level, you can actually fit a relationship to those data, much like you would fit a line. We'll see you all next time, I hope. If you have any other questions for me, you can hang around and ask them. Thanks for coming.